Thank you. Hi, I'm going to talk about feature importances today, and specifically about the LOFO importance that I developed with some of my colleagues at ING, that is open source as well and on GitHub. So let's start out with an example. So some of you may have participated in this Kaggle competition. It's Microsoft Malware Prediction. So Microsoft put a malware data set and asked us to predict whether a machine will soon be hit with malware or not. And one of the features that are in the data set is the operating system version. So that's CentOS OS version. And if you think about it, that should be an indicative feature, a predictive feature, because some versions are more prone to bugs than others. So we probably know this, right? If we train our model on some versions, it will learn which versions are more buggy and which are not. But what if you have data that is, okay, you train the data on, and the model learns on the training data, but then you have a test data set that is like a future data set, and your model hasn't seen this time in the future. So there will be new versions in that data set, and then the model will not be able to know whether these versions are buggy or not, right? So what happens is if you use tree model importances, they typically look at the training phase. They look at the tree structure that is constructed during training, and they calculate feature importances from there. So they would give a very high importance to the version. So for instance, here I got this from a kernel on Kaggle, and you can see that the OS version is the 6th most important version marked by light GBM with the importance of gain. So what else is out there? So the feature importances that are out there are, the first 3 here are specific for tree models. So there's the Gini impurity, there's the gain, there's the split. And those have this problem that I just mentioned. They don't generalize well to test sets. If you have seasonal features, they're not, they might be given falsely high importance. Also, these 3 importances tend to overestimate the importance of very granular features. There's also the Shapley values, or the SAVA score, which is actually quite similar to what we do, and I'll describe that in a bit. But it's only implemented at the moment for tree models. So all 4 of those are very model dependent. And there's also the permutation matrix, which does look at the test set, but it overestimates the importance of correlated features. Enter LOFO importance. So leave one feature out. What we do is actually we want a model that will generalize to unseen test sets, and we want feature importances to reflect that. So the LOFO algorithm first looks at all the features. It calculates the performance metric with all the features in, and then it iterates over all the features, and then one by one it removes them from the model, retrains, and evaluates a cross-validated performance. So what this does is it solves the previous problem that I mentioned, and it's not biased towards the training set. And also what we implemented is that you can put any scikit-learn-friendly model for any performance metric, any validation scheme, and also when you have a feature that could actually harm you if you use it in the training, it will give you a negative importance for it. So if we go back to the example, we have a kernel here on Kaggle, which would show you this. Is it visible? All right. So here we just import the data. We define the target and the features. And the way to call our class is just LOFO importance. You give it the data, the features, the target, the cross-validation scheme. So here we chose k-fold, for instance, and the scoring metric. And if you don't give a model, it will just default to light GBM. And what you get is, for every feature, you get the mean of the importance across the folds and the standard deviation. And so going back to the example of the Microsoft malware prediction, here is the visualization we have for the feature importances. So the colored bar is the value of the mean, so the mean is around here, and then the standard deviation is the black bar around it. And if you scroll all the way down, you'll see that the OS version is actually the most harmful feature, so you shouldn't really include it in your model. Yeah, so that's it. Install it, try it out. It's on GitHub. Just some caveats. It is slow, although we parallelize because you iterate over all the features and it's bound to happen. It's so far still misleading, like the permutation importance when it comes to correlated features, but we're working on that and we're going to implement a leave n features out component, which would then flag all the correlated features and give them the same importance if, let's say, they're very, very highly correlated. Thank you, and also we're hiring data engineers and software engineers.